Good evening. Tonight, we leave the realm of science, the realm of hypothesis testing and peer review, to dive deep into the ancient 37-year-old guild of pixel pushers.
All right, so today I want to talk about what it takes to make relatively clean Landsat composites. And basically, what I mean by that is cloud-free imagery for every year that we have Landsat data. So 1990 or 1984 all the way up to 2022. It can be fairly easy in arid environments, but in most of the world, in like the tropics or in like the east coast of the U.S., it's pretty difficult to actually get the clouds out and create a product that you can actually use for analysis, estimating tree cover or biomass or stuff like that. So the first step that we're going to talk about here is actually not to do anything at all. If possible, I encourage you guys to use a product put up by USGS called the Analysis Ready Dataset. They've already basically created imagery from 1982 all the way to present day for the entire US. And this is analysis ready. So there's no clouds, there's no atmospheric issues, there's no issues of normalization. So it's very easy to just pick up and go with this data set. Of course, we're not all working with, in just the United States. The last that I checked, this data set wasn't necessarily good for what I needed to do. So quite often, almost entirely in my career, I've had to then turn to actually processing the raw data myself. And so if this is what you have to do, we really want to do the processing in a tool called Google Earth Engine. And if you're not familiar with this tool, it's not the same as Google Earth. It's a completely different environment. It is insane. It is suicide for your project to try to process Landsat data outside of Google Earth Engine. One big problem is that the USGS releases kind of raw Landsat data. There isn't a nice repository where you can go and get surface reflectance data for all the Landsat satellites. Now, what do I mean by that? Surface reflectance is not, these are images that have been atmospherically corrected already. So the satellite's flying over the Earth outside the atmosphere. There are different conditions in the atmosphere that cause the light to reflect in different ways, meaning that, on some days, maybe there's more ozone in the atmosphere, and so the red light is going to be absorbed by the atmosphere. Other days, there's maybe more water vapor in the atmosphere, so the blue light is going to be absorbed. So this is a real problem, and you basically need to use an algorithm that corrects for this to create surface reflectance. And the USGS doesn't host surface reflectance data in an easy and native environment. So Google Earth Engine does. So this is why we want to basically start in Google Earth Engine. It's also an incredible environment to actually start programming. Most people don't realize just how much Landsat data there is for any given point on Earth. People have, the Landsat satellites have been basically taking pictures of this at least twice a month for the past 37 years. So you end up with something like 900 Landsat images for a single point, never mind like an area. All right, so we're in Google Earth Engine. Let's actually look at what the differences are between some of these options here. There are two big collections. Collection one is basically just an older set of preprocessed data. You really shouldn't be using collection one at this point. Collection two has surpassed it. It's better. Collection two has slightly better processing. They did a little better job of like geolocating the images and like getting the clouds out of them and stuff. Within collection two, we see a couple of different options. There's surface reflectance, which, like I said, for any genuine analysis product, you almost certainly want to be working with surface reflectance. Outside of surface reflectance, there's the raw images taken straight from the satellite. The benefit to this is that you can get it real time. So if the satellite images the Earth just yesterday, you can get an image. It doesn't need to go through this algorithm that may take a week or two to get surface reflectance. Likewise, there's top of atmosphere, similar to raw imagery, except that there's been a little bit more correction of various like satellite nuances. But for almost every product, you're going to be wanting to work with surface reflectance because it kind of removes those atmospheric effects to the best that it can. All right, so let's look at the actual code for doing this, what I'm doing here is I'm importing all of the Landsat satellite collections. And so I'm importing all the satellites from Landsat 4 all the way to Landsat 9. As I do so, I'm filtering by a geometry. So this is the geometry I'm interested in. I have a function here that masks the image. I basically converted the geometry to a binary mask and used that to basically filter the, basically clip the Landsat image. This is a faster process than using the clip function in Google Earth Engine. So that's why I do it with, like, try to do it all in rasters. I'm filtering the date, and we'll talk about this a bit more later. But essentially, I don't necessarily want leaf off images. If we're working in, for example, North Carolina, there may not be any leaves in the wintertime, and that doesn't tell us much about forest cover. And I'm filtering the calendar range. It's the same deal. I'm renaming the bands. The thing is, the newer Landsat satellites have band names that are different than the old, and so we want to make sure that they're all kind of the same. So I want my blue band to be, band 1, and I want my green band to be band 2. And so that's what's happening here. And then finally, what needs to be done with the newer satellites is the newer Landsat satellites have slightly better sensors, but they're different than the older satellites. And so there are a series of coefficients that are used to basically convert convert from one to the other. And they're called the Roy coefficients. So this is basically a set of like simple regression equations that will take an image taken from a new satellite and make it look like an old, or vice versa. And so that's what I'm doing. I'm basically I'm standardizing the inputs of all the satellites with the Roy coefficients. Now, something to note about the Roy coefficients, they were developed in the United States. They were developed for Landsat 8. So perhaps they're not ideal for the entire world, but they're kind of the only ones out there right now. So we've loaded in basically our raw imagery. We've done a little filtering. The other thing that I'm doing here is I'm removing there's a QA band that comes with this data. And the QA band can tell you whether or not there's cloud cover. It doesn't do the best job. As you can see here, I've loaded in this data and viewed it. There are still a lot of clouds. There's still a lot of like marginal areas as well. So this is why we need further processing. So once this is done, we have kind of raw imagery. It's not quite raw. I mean, it's surface reflectance. It supposedly doesn't have any clouds. It's clipped to our area, and the Landsat satellites have all been, kind of harmonized across one another. So we have this image here. We're not ready to actually start doing any Landsat processing with this image here. This is raw data from the first year. It's not where we need it to be, obviously. And so we're going to advance forward in the pre-processing pipeline. The next thing that I want to talk about is phenology. And what I mean by phenology is that, trees lose their leaves. This happens everywhere on Earth, and you really need to see whether or not you're working in an area where this is a problem. Odds are you are. Even in Brazil, much of the Brazilian Amazon rainforest is deciduous part of the year. And so maybe a third of the trees are actually dropping their leaves during that part. This is a really big problem. Now, what I'd like to do, and the easiest thing to do, is just specify a window. And there's a tool in here that, this function right here will just let you specify a calendar range by Julian date. So you can just say like June 15th to September 15th, take the pixels from that date. That's the easiest thing to do. But if you're working globally, you may not have that option. And then there are a lot of instances in which you can't just specify a window for an area and really get the optimal result. And California is a good example of this because the redwoods on the coast, the majority of the trees that you're seeing in this image are the most green during the winter time when they're receiving rain. The rest of the trees, a lot of the trees that are deep within the valleys of these rivers, for example, are deciduous trees like these guys. And they will drop their leaves in the wintertime. So they are not the most green in the winter. And you really can't look at those trees unless it's the summertime. And then again, there are areas that are just a couple of kilometers away from the redwoods that are covered in snow in the wintertime as well. So we always want to be analyzing pixels during their peak greenness because that gives us the best signal as to, what the actual forest cover is or what the biomass is. But you can see in a scene like this, it's very difficult because you've got kind of like three conflicting desires here. We want redwoods from the winter and we want deciduous trees and high alpine trees from the summertime. What most people do in California is they just take the summer, and maybe their models are taking a little bit of a hit. But you could go pixel by pixel. And so there are algorithms out there that you can basically say this pixel is, reaching its peak greenness in the wintertime. So let's pick pixels from the wintertime. And this pixel is reaching its peak greenness from the summertime. One example of this is basically a data set put out by, I don't know, LPDAC or something, a federal government organization. And what they do is they're using a coarser sensor, but they're basically creating this a map of all of these values here. And so they're creating a map of the date of the year when it reached peak greenness and the date of the year when it was at maturity and senescence. And so you can use this map to actually select pixels that are from their most green period on a pixel by pixel basis. And this is what this map looks like in Google Earth Engine. So it's called MCD12Q2. And you can see here, I mean, what you're looking at here are basically colorations of seasonality. This is the date of peak greenness here. So that's one way to do it. One problem with this map, it's fairly coarse resolution. I think it's 500 meter resolution. So if we go back to here, this scenario where that I pointed out where like inside the valleys, a 500 meter pixel is going to cover this whole thing. So it's not necessarily ideal. The other thing you can do, you can dive into like the actual Landsat phenology and try to recreate this map yourself using Landsat. This is something I've done in the past. And it can be made to work, but it's something that you kind of require some time and research. Once again, if you have the luxury, I would say just specify a growing season. When I'm working on the East Coast, I specify it's the summertime, right? All right, so we've handled how people cover that, and I'm just specifying a growing season from here on out for the work that I'm doing in the Amazon for this example. The next thing that we need to do is basically we want to create a set of annual composites. And so what I mean by that is that instead of having like all the images for all the years, we want to create like a set of median values for every year. So 1984 has a single image with kind of like the best characteristics. 1985 has the best image, rather than just having like hundreds of images in a stack. How we're going to do this is in Google Earth Engine, we're going to use like basically a loop, and it's going to loop over every year. And for every year, we're going to take the Meteoroid. What is the Meteoroid? The Meteoroid is basically a fancy median. So whereas a median will take the median value for each one of these bands. It'll take the median value for green. It'll median value for red and for blue. A meteoroid will compute which image has the most median values in the image stack, and it'll take that whole image. And the reason that we want to do this is if we take just the median, then the ratios between like the blue and the red could be thrown off because one of them could be taken from one image and the other one could be taken from another image. This is really bad because we use the ratios of these colors to actually do analysis of the forest. So we take the meteoroid because we're getting like an actual genuine observation of the Earth. Now, we don't have to be intimidated by the actual function. It's pretty simple. It's just like calculating the median and then taking the image that has the lowest difference. And so from that, we now have, what you're looking at here is basically an image from the year 2000. And it's a lot better than the first one, right? So now we have taken the median image, the meteoroid. And still, though, I'm not satisfied, right? Like all these clouds, in an area like this with cloud cover, if I tried to apply a forest cover map to it, it would say that there's no forest cover, right? This is not good. So, we're perfectionists here. We need to really hammer out as many of these clouds as we can. So we're going to move on to the next step after this. After this, what we are going to want to do is run these images through an algorithm called Landtrender. Now, Landtrender is basically a line fitting algorithm. We've got all our images in a time series from 1984 to present day. And each one of those has, red, green, blue values associated with them. And what Landtrender will do is it will fit that time series and fit a series of lines that basically go through the middle of them. There are two reasons we need to do this. The first is that Landsat imagery, it's just by nature, it's fuzzy, right? Like red, green, blue, it could go up and down by 10% in a given year. That means that your forest cover model goes up and down by 10% in a given year. And this is not okay. So we need to fit a line through the middle of that. the other reason is it'll remove those clouds, right? This is a further step that will remove outlier years. And so by fitting a line through that, we're going to take the values of that line. We're not going to actually take the values of a particular year. And this is kind of a necessary step to create cloud-free images. And it's very common. Everybody uses this algorithm. I would point out this algorithm is created by Oregon State by Robert Kennedy, who has done a lot of work in terms of making Landsat data usable. So how does this algorithm work? It's got to be run over a single band of data. So we could run it over like our red band, our blue band, our green band. What I like to do is run it over normalized burn ratio, which is a ratio between the near infrared and the far infrared bands. And I like this ratio because it's basically an analog for forest cover. And so it's going to fit this analog for forest cover really well. And then it's going to use that model to assign values to the red, green, and blue colors as well. And so this is the complicated stuff that goes on behind it. In order to get the actual values fitted along the line, you've got to like use Google Earth Engine with array math. This is the algorithm itself. It's got a bunch of parameters. I wouldn't be scared off by this. These are the parameters that are just recommended by Robert Kennedy and his lab. So they've done a bunch of testing to make sure that these are kind of the ones that you want for doing this. The other thing we have to do is set a date for our images, right? So we took the bunch of images from a single year and made them into one. We're going to set the date as just the middle of that year. So like August 8th is like the middle date of a year. One thing to note here is that I only do this once, right? So I run this over normalized burn ratio and use those lines to get values for all the other bands for red, green, and blue. A lot of people will run this multiple times, and they get better results that way. If I were to run this like 3 times with NDVI, normalized burn ratio, and the green band, I would probably get a better long-term average, right? And probably fewer clouds and better everything. But Google Earth Engine, it's slow. So I don't necessarily want to do it. So I'm just running this the one time. And you can see here, our composites now, our annual composites for the year 2000, they look a lot better, right? There's really not any clouds left in here. Great. So this is pretty much where we want to be at to make, at the very least, pretty pictures. And now we can use this to actually make some nice movies of like what happened over the Amazon in the past. But we're not done yet. I'm afraid that there are more problems to face. If you are in the modeling space, now a lot of people will just stop right here, and this works for a lot of the world, but it doesn't. It's not quite good enough for the tropics, and one of the reasons for that is that the Earth is getting greener. This is a well-studied phenomenon. Trees are getting greener. The reason for this is that the Earth is warming. There's more CO2 in the atmosphere, and there's more capacity for photosynthesis to take place. So we can observe the Earth getting greener by just looking at the normalized burn ratio for the last 36 years and just looking at what's happened in the past, right? And so there's this upward trend. You can see it. And I just randomly picked a pixel on this map outside of Manaus in Brazil. And it's getting greener. And this is, like I said, very well-studied phenomenon. There are many papers on it. There's papers from Nature. So, yeah, this is a real phenomenon that's happening. But it's really bad for us who are trying to make models of forest cover or biomass or any of that, or like forest typing. It's really bad because while the Earth may be getting greener, the trees are not growing at the same pace. So the Earth has gotten at least 10% greener in a lot of these areas over the last 40 years. The trees have not been able to add 10% more carbon, right? And for the most part, like there's not 10% more tree cover. And so if I apply a model that was trained, on data from 2020 all the way back to 1984, it's going to estimate that there's like at least 10% less tree cover in 1984, which it was not the case, right? Quite the opposite, probably. So this is a controversial bit, but when I'm working in the tropics, I will remove this trend because it's the only way that I can create, models that work in the tropics just as well in 2020 as they do in 1984. So the way that I remove this trend is and I'm not the only one who does this. Many people will basically normalize all of their year's imageries so that the values for all of their years are kind of set to the values of a particular year. Now, one way of doing this is to normalize your imagery to MODIS observation. So MODIS is a satellite that's been in orbit since the year 2000. This is a good way to kind of make sure that everything is kind of level. Because MODIS observations, it's been taking a picture of the Earth every single day. There's like a good repository. I don't do that because I need to go back all the way to 1984 for a lot of my work. The other alternative is to basically normalize all your images to a single image, or basically in this context, normalize all your images to like a single year. So, a lot of people will say, let's normalize all our images to the year 2000. And what I mean by that is that we're going to compute the ratio difference between basically areas that haven't changed, so forested pixels. And we're going to say, okay, a pixel from 2020 has 5% more, is 5% more green than it was in 2000. And a pixel from 1984 is 5% less green than it was in 2000. And we're going to then adjust the values so that the line becomes flat. Now, how do we do this? One of the first things that we need to do to actually do this is find pixels that have not changed. Now, a very popular way of going about this is called dark object subtraction or dark object normalization. And people like doing this because if you can find dark objects like water, for example, this is potentially a good target that has not changed over the decades. And this is, you can then use the values from those pixels to normalize all the other values. You can normalize the entire scene, but if you're normalizing pixels that have changed themselves, so if the Brazilians have cut down a bunch of trees here, then you're potentially like normalizing the wrong pixels. They're potentially making clear cuts look more green. So in some way, we have to basically isolate pixels that haven't changed and normalize the rest of the time series to make it look like, to make them all kind of have the same values. What I do to actually do this is I will identify pixels that haven't changed over time. There's an algorithm that basically runs Landtrender a second time and looks for instances in which there's been no change to the time series, in which we have a single flat line on Landtrender. And it'll pick those pixels, and then it'll compute a series of normalization coefficients to say that an image from 1984 was 5% less than the image from 2000. So that's how I do it. I have the second Landtrender run that's built in. Like I said, there's a variety of ways of normalizing images. You can use MODIS. You can pick dark objects. So we're getting these normalization coefficients, and then we're basically flattening the time series and making it so that we're putting all the greenness at the same level for every year. This doesn't get rid of deforestation. If deforestation takes place, it's still going to be like a dramatic difference in the greenness. But what it does is it makes sure that forests that were forests the entire time have the same value the entire time. Like I said, this can be controversial because, a true physiologist or someone would say, the forests aren't the same. This is an actual observation. You can't just throw it out. But in practicality, we can't be using data that changes by 10% over the course of a time series. The other thing that I do, I'm not interested in water, so I filter it out. I'm not a marine biologist. My wife is a marine biologist. But the way that I do that, there's another layer in Google Earth Engine that I just use as a mask, and it's a pretty good layer. So yeah, the JRC layer is a pretty good, and it's conservative as well. So it's only removing permanent water bodies. And so this is the finalized product that we have. We have these very nice, clean, cloud-free images for every single year in one of the most cloudy places on Earth. And this is how I now go forward and create my tree cover maps and create my land cover classifications and stuff. This is a set of algorithms that are used by a bunch of people. I mean, this is basically what Oregon State does and what a lot of the insiders in the industry will do. But it's a brutal set of algorithms if you aren't familiar with Landsat pre-processing. So hopefully I'm shedding a little light there, making it a little easier to understand what's going on in the background for a lot of these groups.